Thanks for being here, and thanks to the organizers of this symposium, in particular to Carlos and Luis for inviting me to give this short course in Essentials of Black Hole Electrodynamics. Well, I guess, as you can read from the title, we will talk about electrodynamics, which means that we will talk about electromagnetic fields and charged matters, which will react to these electromagnetic fields. Here we have the additional difficulty, complexity, that we are in a curved background, so we will have some effects related to black holes. Of course, feel free to stop me and ask any question. So let's start from the beginning. So why do we bother about black hole electrodynamics? And the reason is that, well, this is the theory underlying some of the most extreme phenomena that we can observe in the universe. One example is the emission of the relativistic jets. No, sorry. Okay, I got a pointer. Oh, yes. Okay. One example is the emission of the relativistic jets, as you can see from these pictures. And these are extremely energetic and collimated streams of plasma, which propagate for impressive distances in the extragalactic medium. And just to give you an example of how energetic these jets can be, we can look at this picture, which is called the Death Star galaxy, which is called like this because it's it reminds about the Star Wars movie. In this case, we have a jet emitted from a black hole, which is basically disrupting another galaxy in the nearby. So this should give you a feeling about how energetic these jets can be. And the point is that the origin of these jets is basically at the center of the active galactic nuclei, which we know now as supermassive black holes. And we know this also because we have taken some picture of them. So M87 is a perfect example of an active galactic nuclei. And we have to remind that whenever we look at this picture, we are not only looking at the very first image ever taken of a supermassive black hole, but we are also zooming in toward the region where this jet is emitted in first place, so we can understand many important features of the emission mechanism. For instance, you can notice that the light coming from this region is polarized. The signature are these kind of strips here. And the polarization is a smoking gun signature of the presence of a strong magnetic field in the black hole environment. So already at this level, we are learning something. So black holes are not, astrophysical black holes at least, are not isolated objects. They are immersed in an environment which is a soup of plasma and strong electromagnetic field. And because of this environment, it is possible to have effects such as the so-called Blandford-Snark mechanism, which can extract the rotational energy of the black hole and convey this energy to power these relativistic jets. So we will see, we will discuss the Blandford-Snark mechanism as the end point of this short course, but basically, long story short, this is an example of an electromagnetic manifestation of the Penrose process. We have other examples of black holes photographed by the Event Horizon Telescope, Sagittarius A star, for instance. This is not an active galactic nuclei. There is no jet associated to it. Nonetheless, its phenomenology is quite interesting, and we can anyway notice that also this picture shows polarization, which means that also Sagittarius A star is immersed in a magnetic field. And you can also notice that there are bright spots, 3 bright spots that are basically absent in the other image of M87. And it is supposed to be that these bright spots are actually related to magnetic effects related to a process called magnetic reconnection, which generates flares. So eruptions of magnetic field and plasma, similar to the one that we observe in the solar corona. So my point is that if we want to understand these pictures, if we want to understand what is the physics behind it, we need to understand how magnetic fields and plasma behaves in the strong gravity environment generated by the black hole. And this is the main reason of this course. So this is a very quick outline for what we will see, and today's lecture, I hope it will not be very boring for you, but basically we will introduce all the elements which are important in this context. So black holes and energy extraction and electromagnetism in curved space-time. So let's start with black holes. Of course, needless to say, these are solutions of Einstein's field equations. So we have the geometry, the curvature tensor on the left. These are related to the content of the space-time, which is on the right and encoded in the energy momentum tensor of matter. Is it too loud? Is it? Oh, okay. 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 And the first clue that black holes could be real astrophysical objects came with the idea that this can be formed via gravitational collapse. So the idea is basically to have some sort of distribution of matter. Doesn't really matter what form of matter it is. The important thing is that it's subject to its own gravity and will start a collapsing process. If this collapse is not counterbalanced by any other repulsive forces like nuclear reactions or the Fermi interaction, then the collapse will proceed indefinitely until we form a black hole surrounded by non-equilibrium particles and fields. Since this is a non-equilibrium system, it will start to emit radiations. And in particular, we will have radiation which escape towards infinity, and radiation which will fall into the black hole, feeding the black hole with additional energy and angular momentum eventually. The point is that through this radiation process, first of all, we reach a vacuum solution when we basically consume all the matter in the surrounding of the black hole. And through this radiation process, the system will reach a stationary and axisymmetric phase. And stationarity and axisymmetry are basically symmetry statements, which in general relativity are encoded by the existence of a certain class of vectors called Killing vectors, which obeys this important Killing relation. And in particular, stationarity and axisymmetry are associated to time translation and rotational invariance around a certain rotational axis. So the end point that we reach is therefore a stationary and axisymmetric solution of Einstein's field equation. And the content of the no-hair theorem is precisely that this endpoint will have radiated away all the hairs, all those characteristics which are not intrinsically related to the mass, the angular momentum, and the electric charge of the black hole. So the final state that we reach is always, at least in general relativity, is always a Kerr-Newman type of black hole. Of course, we expect astrophysical black holes not to be charged, or if they are, they will have a very little charge, not capable of producing any significant gravitational effect. So as a first approximation, we can consider the Kerr space-time as a good representative for an astrophysical black hole, which represents indeed a black hole characterized by a certain mass and a certain angular momentum. Of course, there are important regions in this space-time, so since this is a black hole, it is characterized by an event horizon. We have a symmetry axis, which is the rotational axis of the black hole, and which is basically orthogonal to this plane called the equator. But in spinning black holes, we have an additional important region, which is the ergosphere, the ergo region. And this ergo region plays a prominent role in energy extraction mechanism because by means of this region that we can create objects with negative energy, as we will see in a moment. So just to recap some important idea, often in general relativity, it's important to adopt the perspective of certain convenient observers. One of these observers is called typically the normal observer, which is normal to constant time slices of the space-time. It is also in stationary and axisymmetric black holes like this, it is also often called the zero angular momentum observer. And using the perspective of the normal observer allows us to decompose the space-time into an absolute time and to an absolute space as referred to this observer. So in this 3+1 decomposition, basically we can write the metric in terms of 3 physical quantities, each with a proper interpretation. So the first quantity is the lapse function, alpha, which is associated to the curvature in time. Basically, it states that it's a statement related to the gravitational redshift. The more we are closer to the black hole, and the more time will pass slowly. Then, if the black hole is rotating, we have an additional term, which is called the shift vector. This is associated to the frame dragging effect, namely to the fact that if the black hole is spinning, then it will drag into the spinning motion also the surrounding space-time, which means that the surrounding space-time possesses an intrinsic angular momentum, which will be inherited by every object which is placed in this space-time. Finally, we have a spatial metric, which is associated to the curvature in space, and which is basically related to the deviation of the trajectories in space for particles and light rays around the black hole. So basically, these 3 quantities characterize the entire metric and characterize all the strong gravity effects that we need to discuss. But now let's proceed to understand why it is important, what is the role of the ergosphere, and how it is possible to extract energy from a spinning black hole. The idea is basically that of feeding the black hole with some form of negative energy. And this is clearly illustrated by the Penrose process, in which we have a single particle which enters the ergosphere of a curved black hole, where it decays in 2 other particles. One particle will be created with negative energy and will fall into the black hole horizon. Then we have another particle escaping at infinity. And since energy is at the end conserved, this particle will gain an additional energy which directly comes from the black hole rotation. So this was the first example which illustrated the way in which we can extract energy and angular momentum from a spinning black hole. But it is important to realize that this is not the only possibility. Other possibilities were then discovered in the literature. We can have superradiance, so some sort of scalar field around the black hole will have modes amplified by the black hole rotation. This is not, I had a conversation yesterday with Carlos about this. This is not intrinsically related to black hole physics. It's an effect which is more general, but we can also have it around the black hole. And more astrophysically relevant is the Planck-Forsznajek mechanism, which I was telling you about. In this case, the agent operating the energy extraction will be a very strong magnetic field, which we call a magnetosphere, which spins together with a black hole such as to tap continuously its rotational energy, which will be used to power the relativistic jets, which we have seen before. So we have different possibilities, and actually all these possibilities can be fitted into one single framework, that of generalized Penrose processes. In order to have a generalized Penrose process, the only thing that we need to have is some conserved form of energy and angular momentum encoded by an energy momentum tensor, and some Killing vector, which is natural to have in a black hole space-time. We can combine these two to form two conserved currents. These are essentially Noether currents associated to the symmetries of the space-time. And since these currents are conserved, we can integrate them to obtain an integral form for a conservation law, an integral form which will be associated to the conservation law of energy and angular momentum, essentially. So we can perform this integral. We integrate the gradient of this current over a certain portion of the space-time. And by means of the Stokes theorem, we can always convert this integral, which is a volume integral, into an integral over the surfaces, over the boundaries of this volume. And in this example that I'm showing, the boundaries are represented by two time slices, one in the past of another. Then we have, so the green region is the ergosphere, basically, and this gray region is a portion of the event horizon, which can always be foliated as a two-sphere times a certain amount of time which requires the process to occur. Finally, we can have in principle an external space-like surface, but this is a boundary which can be pushed at infinity and doesn't play any role, essentially. So we can basically evaluate this integral by computing the fluxes over these boundaries. And what we obtain when we compute the flux over the time slices are basically the energy contained in that time slices, which means the energy contained in the space-time at that precise moment. We can also compute the integral over this gray surface, and what we will obtain is the influx of energy at the event horizon. So once we have this, we can just write the integral form of the relation above, and which will show that the energy contained in the time slice in the future can be greater than the energy contained in the time slice of the past if and only if the energy inflowing through the event horizon is negative. And this is essentially what happens, for instance, in the Penrose process by means of particles. But this construction is totally general. We never specified that we are talking about particles. This can be every energy momentum tensor associated to any field. We just need to identify a process for this to happen. And in particular, instead of considering single particles, so instantaneous events, let's say, we can also consider continuous processes like the Blandford-Esnaich mechanism, for instance. So this was enough for what we need to know about let's say, black hole physics. Now we can start to discuss electrodynamics in curved spacetimes. So, of course, what I am going to say is not directly related to any black hole spacetime. This can be associated to any background metric, basically. And we just need to recall some fundamental things about our special relativity class. So an electromagnetic field is the true entity which is a frame-independent quantity in relativity. It's always represented by a rank 2 antisymmetric tensor. We can also, by means of Hodge dualization, which is this contraction with the Levi-Civita tensor, we can always construct a dual field. And sometimes it is convenient to just, split the electromagnetic field in electric and magnetic field, because our mind probably is more used to think in terms of three-dimensional objects, even though the true frame-independent quantity, the true relativistic object, is the electromagnetic field on its own, represented by the Faraday tensor. So just can I? just recall what we do in special relativity. So what we do, basically, when we write the Faraday tensor as two matrices, is to identify the electric and magnetic fields as the time component of the Faraday tensor and of its Hodge dual. Now, in general relativity, we don't have a unique time direction. This is true also in special relativity, actually. But basically, what we can do is to mimic the same logic. So we can choose a certain time-like observer. This will define a certain time direction to follow. And then we project the Faraday tensor and its dual over this time direction. The result will be essentially the electric and magnetic field as measured by that specific observer. So this is a sort of covariant definition, if we want, of electric and magnetic field, but it's always referred to a specific kind of observer. And by means of this, we can also like decompose the field strength and its dual in terms of these quantities. So in terms of electric magnetic field and the force velocity of the observer. Now, precisely like in the case of particles, we can, or in the case of vectors, more generically, we can classify vectors in terms of invariance. So we can say that a vector is time-like, space-like, or null, depending on the value of its squared module. And similarly, we can also classify electromagnetic fields in an invariant manner. So what we can do is to construct Lorentz invariants, and basically the first invariant that we can logically construct is the square of the Faraday tensor. This is associated to the difference in modulus of the magnetic field and the electric field. Now, we can say that a field is magnetically dominated if this object is greater than 0. And since this is an invariant statement, if we compute this in whatever observer is convenient for us, this will be a magnetically dominated field for every observer. So a magnetic field always exists, is a physical, true physical quantities, if we want. For magnetically dominated fields, we can always make the electric field vanish, but never the magnetic field. And these are very important. These are the fields that are more important in astrophysics, of course, because in astrophysics, we have to deal with neutral objects. So typically, we don't have unscreened electric fields. Another invariant that we can construct is this one, the contraction of the Faraday tensor with its dual. And basically, this is the projection of the electric field over the magnetic field. In this case, we can say that a field is degenerate if this invariant is equal to 0. Actually, degeneracy implies a series of mathematical assumptions which are very of mathematical consequences which are very interesting, and maybe I will discuss about this tomorrow. I'm not sure, but the idea is that since there's an invariant quantity, if an observer measures an electric field which is orthogonal to a magnetic field, this will be true for every observer. And this is also the kind of fields that we look for in astrophysics, because typically we have to do with plasma, and a plasma is a sort of conducting fluid. And as you know, in conductors, we never have an electric field internal to the conductor, because the electric fields will, the electric charges will move in such a way as to screen these electric fields. So this is basically the ideal field that we expect in our astrophysical plasma. Now, we have discussed about the structures of the field. We still need to understand what are their equations of motions. Obviously, these are the Maxwell's equation and the curved space-time. We can just substitute the derivatives in terms of the covariant derivatives. The first equation is automatically solved by introducing a certain gauge potential. The second equation is the non-homogeneous one and relates the electromagnetic fields with matter. So matter here is represented by a 4-current density and has a dual role. It can be the source of the electromagnetic fields, so the source of these differential equations, but it can also be the matter reacting to some external magnetic field, electromagnetic field in particular. As if we want to adopt the 3+1 decomposition that I mentioned before, it is possible to do this, and the Maxwell equation takes a very familiar form. So these are basically the Maxwell's equations which are used to see in our classical electrodynamics class. The only thing is that the constitutive relations are now relates these fields in terms of the lapse function and the shift vector. So in this sense, the general relativistic version of the Maxwell equation reminds of the Maxwell's equations in the medium. So this is a standard result of black hole electrodynamics. So in the sense, we can think about the lapse function, the redshift factor, if we want, as a sort of vacuum permittivity for the fields, whereas the shift vector is always associated to some sort of polarization or magnetization of the field. Finally, how it is that matter interacts with electromagnetic fields, of course, through the Lorentz force. We can estimate the Lorentz force by computing the gradient of the electromagnetic energy momentum tensor. If matter is present, this will not be conserved in general, and the non-conservation is encoded by this term, which is precisely the Lorentz force. Now, if we are in vacuum, the Lorentz force is 0 because obviously we have no matter. There's actually another case in which this term is negligible, and it is the case of force-free electrodynamics, which is the theory that I was mentioning during one of the questions today. Because force-free electrodynamics applies when we have a very strong magnetic field which overwhelms the plasma in the energy and momentum balance. I will discuss about this tomorrow or the day after probably. But basically, by imposing this force-free constraint, what we obtain is a highly nonlinear regime of Maxwell's electrodynamics. As you can see here, the field appears multiplied by its derivative. So already at this level, we can have some sort of nonlinearities in the theory. Typically, in astrophysics, we are interested in matter, which is in the form of gas or fluids or plasma, if we have electromagnetic fields. And the theory describing this type of dynamic is the relativistic hydrodynamics, which we can consider as an effective field theory in the field theoretical sense. So it is a long-distance dynamic in which we fix a certain length scale and we integrate out all the dynamics which is below that cutoff. So the dynamical equations of relativistic hydrodynamics are the continuity equation and the energy and momentum conservation. We need to specify some dynamical field, which in this case will be a 4 vector associated to the 4 velocity of the fluid and a scalar associated to its temperature. And then we have to decide how the two conserved currents will relate to these fields. So this is the content of the constitutive relations, which in the field theoretical sense can be interpreted as the leading order term of a derivative expansion, so of an effective field theory derivative expansion. Actually, in order to close the system, we need to add thermodynamics. So we need an equation of state telling us how the pressure behaves in terms of the temperature, because these are thermal degrees of freedom. we need a first law of thermodynamics, and the second law of thermodynamics is used to constrain the form of the constitutive relation. In particular, the derivative corrections are those associated to the production of entropy. And in this theoretic approach to relativistic hydrodynamics, then the derivative corrections are basically associated to the transport properties of the fluid. But this is a long story. Now, we are, of course, interested in the case in which we also turn on electromagnetic fields. So the theory that we obtain by combining the Maxwell's equations with relativistic hydrodynamics is called relativistic magnetohydrodynamics, which is the theory which we typically use in astrophysics. So here we have to add the Maxwell's equations. We need to correct this equation with the Lorentz force, and of course we need to add additional dynamical fields, which are the electric and magnetic field. We need to choose some observer because these are not covariant quantities in principle. And a logic observer to choose is precisely the observer co-moving with the fluid. So the additional objects, the additional fields that we add are the co-moving fields. Now, if we have a plasma, as I said before, typically we are talking about an ideal plasma, so a sort of ideal moving conductor. In this case, we don't want to have any electric field. So we can simply set it to 0. This is an assumption. This is a working assumption, which allows you to derive the regime called ideal magnetohydrodynamics, or MHD for short, for which we can write basically the total stress energy tensor of the system solely in terms of the force velocity of the fluid and the magnetic field that the fluid that generates the fluid and to which it reacts. And the same is true for the dual field strength, and therefore also for the normal field strength. So this is basically the setup that we need in order to address typical astrophysical problems in relativity. It is covariant. It can be applied to any metric, to any background. And this is basically the type of equations that we are going to solve numerically when we want to address some of the astrophysical problems like black hole accretions. So in this case, what we do is to put these equations into a computer, make some assumptions, and let the equations evolve. And this is precisely the way we can simulate the dynamics of the accretion flows around, for instance, M87, which we can see here, or maybe better here. So in this context, what one does typically is to fix the background. We keep the background as if it is the Kerr metric, and we just put matter. We inject matter and let the matter evolve and follow the dynamics of the background. But there are actually cases in which this is not a possible assumption to make, because the matter and the electromagnetic fields are so intense that they also contribute to the curvature of the space-time. They contribute to a space-time back reaction. This is the case in which we have to plug the energy momentum tensor of MHD inside the Maxwell field equation and let the entire system evolve. This is a problem which you cannot address analytically. And this is, for instance, the case of neutron stars merger. So here we can see some simulations where we see the coalitions of two neutron stars and the consequent formation of a black hole with the emission of the relativistic jet by means of the Blunt-Forest-Nyack mechanism. And I think I can conclude now here for the moment. I don't know how much time I have left. 10 minutes. Okay. I don't know. We can also conclude here. I think we are all happy to go home before, right? Also,
So, do we have any questions? Question.
Thank you for the very nice lecture. I have a curiosity with these informations that you gave in the end by the metrics not fixed, the background's not fixed because the electromagnetic field reacts. So, do you have some estimation from the numerical data about the difference between, for instance, Kerr-Newman or Kerr to the numerical result?
yeah. Okay. First, First of all, I'm typically an analytic guy, so I don't typically have numerical informations, to be honest. If I get your question, what you are asking if is the final black hole, is it a Kerr-Newman type or a Kerr type, or if it's something else. So this is an information that I have. So the simulation that we are showing here, which are done with Bach, it's a code realized in Frankfurt. Basically, what they show is a black hole which is consistent with Kerr when it reaches stationarity. Of course, you have a phase in which things are not clear, because before you reach stationarity, you have a large, it's not even clear how to define an event horizon, basically, um, at least in simulations. But the final result is perfectly consistent with Kerr. Yeah, after stationarity is reached. Uh, Probably is also, but this I'm not sure. I don't want to give false informations, but there's probably some constraint that imposes like flat space-time asymptotically. Like, of course, you cannot speak about asymptotics in numerical simulations because you have a finite boundary. But I think that there is some sort of boundary conditions there, and that might imply that your final result cannot deviate too much from Kerr. Definitely, what I can say is that this is not a Kerr-Newman black hole, or that it doesn't have a very large electric charge.
Any other questions? So let's thank Philippe again.